Hi again. So this video is going to be about section 10.9, which is deviations from the ideal gas law. There's one more section in this chapter, but instead of doing the chapter reading, you're going to have a POGL for that. Okay, so the reason why we call it the ideal gas law is because if that is when we have exact conditions that the gas wants. Unfortunately, that's not how it works in real life. So let's talk about what real gases act like. Okay, so real gases do not behave ideally at high pressures, okay? So if we look at this graph, so first of all, it says why? Because molecules will attract each other. So if we think about gases take up all of the space that's allotted to them, okay? So if we increase pressure, you have to remember that we're also then decreasing volume. And what happens when we decrease volume is that you're compressing the gas particles closer together, and they don't like that because gases don't like touching each other, right? They're kind of the antisocial molecules of the periodic table. Okay, so what we're seeing here is that this is showing me right here. No, why did it take me to the next slide? Go back. Okay, this right here is showing me what an ideal gas should be doing at a consistent pressure, or a rising pressure. So ideally, it should stay right here. Okay, now, realistically, though, our real gases and how they actually act is what we're seeing with these other three lines, okay? So we'll notice as pressure increases, depending on what gas we're talking about, the slope of the graph goes up, okay? So we're getting further and further away from that one. It also then depends on temperature, okay? So if temperature is low, we also have high deviations, okay? So let's think about this. Pressure, the molecules got closer together. Temperature-wise, if they cool down, they can't move as fast. So then that means they're gonna have more interactions, which is what I kind of say here. As you cool gas, the kinetic energy, which is the movement, decreases, but the attractiveness forces remain constant. And then the gases cannot overcome this attractiveness, okay? So with this graph, it's the same thing, and we can look at these temperatures here. Ideally, it should stay here, but what we're seeing is the lower the temperature, the further I am away from the ideal gas, right? 1,000's getting closer because that's the highest temperature, right? So if we're putting these two things together, what are the two things that will make an ideal gas a real gas? And those two things are temperature and pressure, right? Because the attractiveness of the gases doesn't go away. Okay, so let's talk about that then. So therefore, this should say real gases, therefore, real gases prefer high temperature. Why? Because they can spread out further, okay? Low pressure, because there's more space for them to move, right? Because if we have more pressure or low pressure, the volume becomes bigger. Oops. Okay, so let's kind of look at this here. Don't worry so much about the intermolecular attractions. We haven't really talked about that yet, okay? I keep going forward. I'm so sorry. So over here are the conditions that a gas prefers. So high temperature, low pressure, okay? The particle size, small compared to the space between the particles. So then the interactions between the particles become super insignificant, right? Because they're not attracting each other. Now, over on the non-ideal, which is what we call real gases, they're working at low temperatures and high pressures. So the particle size significantly compared to the space between the particles. So you'll notice that we have more particles, right? And then interactions between particles are significant. So ultimately, we don't want gases to interact with each other, but unfortunately they do. So we can't always use the ideal gas law. So what do we use if we can't use the ideal gas law? Now, mathematically, you're not going to have to know how to do this, but if you move on and take chemistry in the future, this will be an equation that you'll have to know, but you don't need to know it for the AP test. So it's van der Waals equation for real gases. So you'll see that we have all of the things that we had from the ideal gas law. We have pressure, we have volume, which is right here, and then we have nRT, which is our moles constant and temperature. But you'll notice that there's two different things that we have to account for if we're talking about a real gas, okay? This right here accounts for the attractive forces. Okay, so we have to remember that gases don't want to be attracted to each other, but unfortunately they are. So what this does in the equation is it accounts for the attractiveness that the gases will have for each other. And then this, the NB, is the space gases take up, right? So let's look at this. So if I'm adding something to pressure, right, that's ultimately making the pressure increase, which is what we want, okay? And then is making the pressure increase, which is what the gases don't want. So this is us accounting for the increase in pressure, okay? And then this NB is the space that the gases actually take up, okay? And so that means that if we have an original volume, we are subtracting the space that the gases are within, okay? And that's how we're gonna get a closer account of what a real gas looks like as opposed to an ideal gas where we just use PV equals nRT. Okay, that's it for this video. Thank you.